Okay, we have an assembly comprised of a hoop fastened to a rod. The bottom of the rod is connected to a rotation axis. This assembly starts off motionless in the vertical position. You walk up to it, give it a little nudge, so it starts to rotate about that rotation axis. We need to find the angular speed of this assembly when it is at the very bottom of this swing, when it's perfectly inverted. Here's a rough animation showing what's going on. The assembly has 0 angular speed at the very top, and as it swings, it attains a maximum angular speed at the bottom. Our job is to find the value of this maximum angular speed. I'm going to take a conservation of energy approach. The total mechanical energy of this assembly at energy state A, which is this vertical position, plus whatever non-conservative work is done by one or more non-conservative forces, is going to equal the total mechanical energy at energy state B, which I'm calling the bottommost or inverted position. Mechanical energy just refers to the total amount of kinetic energy and potential energy, and in this case, the potential energy is gravitational potential energy. The object starts from rest. It's located at what I'm designating as the base position right here. You got to start somewhere. And I'm specifically going to say wherever the center of mass is of this assembly, when the assembly is at its vertical position, that's baseline. Baseline is where the gravitational potential energy equals 0. There are no non-conservative forces doing non-conservative work, so the entire left side, this entire left side right here, becomes 0. 1/2 I omega squared is the rotational kinetic energy term for the assembly. mGHB is the gravitational potential energy term for the assembly. I know when the assembly is vertical, I have 0 rotational kinetic energy, and I know when the assembly is at its bottom position or inverted, it has a maximum amount of rotational kinetic energy. Similarly, I know at the baseline, I have the maximum amount of gravitational potential energy, which in this case is 0. Sounds kind of funny, but that's true. And at the bottom position, I have the least amount of gravitational potential energy. So I can see my assembly is swinging from 100% gravitational potential energy at the very top to 100% kinetic energy at the very bottom. Between the very top and the very bottom, I have a blend of rotational kinetic energy and gravitational potential energy. When I isolate omega in this equation, this is what I get. Capital letter M is the combined mass of the hoop and the rod, G is the acceleration due to gravity, and H sub B is this bottommost position, which turns out to be negative 4R. More on how I got negative 4R in a moment. Let's talk about rotational inertia I. We have a compound object that's comprised of a hoop connected to a rod. So the overall rotational inertia of this object is the rotational inertia of the hoop plus the rotational inertia of the rod. Here's a table of inertias taken from the Halliday and Resnick textbook. My first question is this the type of hoop that we have, or is this the type of hoop that we have? I'll go back and look at my object and I can see that based on this layout and how it's rotating, this is the hoop that I'm working with. Except in my case, the hoop is not rotating about this blue central axis going through a diameter. It's rotating about an axis that's parallel but offset from this axis, which is why I'm going to need to use the parallel axis theorem. I also have a thin rod, but similarly, it's not rotating about this axis. It's rotating about an axis that's offset to this and parallel with it. This is another job for the parallel axis theorem. My green sheet lecture notes provide the derivation for the rotational inertia of a rod, 1/12 mL squared, so check it out. Also from my green sheet lecture notes, here's the parallel axis theorem derivation. For this particular object, if this is the axis of rotation going through the center of mass, and this is the offset and parallel axis about which it's actually going to rotate, then I get this expression for the rotational inertia of this object about its new offset and parallel axis. Okay, for the rotational inertia of the hoop, we have 1/2 mr squared plus md squared. D is the distance from the center of mass, axis of rotation, which is the axis of rotation that is aligned with this diameter, and the new offset parallel axis, which is this rotation axis right here. So the value of D is this distance r plus this distance 2r, or 3r is the value of D, the offset distance between the center of mass, axis of rotation, and the new offset parallel axis of rotation. So the rotational inertia of the hoop about this axis of rotation is 19/2 mr squared. I'm using m because the mass of the hoop is the same as the mass of the rod, and we're just calling that m. Okay, here's the rotational inertia of a rod, 1/12 ml squared. Again, this was derived for you in my green sheet lecture video. I have to use the parallel axis theorem, so I need to add this term, md squared, because the rod is not rotating about its center of mass axis of rotation. It's rotating about this parallel but offset axis of rotation. So the value of D is from here to here, or in this case, D equals R. So the rotational inertia of my rod is 4/3 mr squared. Again, remember the mass of the rod is the same as the mass of the hoop, and we're just going to call that m. So the total rotational inertia of this compound object, which is comprised of a hoop and a rod rotating about an offset axis, is 65/6 mr squared. Okay, we know I. Let's move on and find m, the mass of this compound object. We simply add the mass of the hoop and the mass of the rod. They each have a mass m. So the total mass, the m term, is 2m. Capital letter M equals 2m. Now let's find this h subscript b term. H subscript b is the height of this object at energy state b, which corresponds to the inverted position of this compound hoop and rod. As far as positions are concerned, I need to find this compound object's center of mass. The center of mass is the point where all of the object's mass can be considered to be concentrated. This is the expression for the center of mass. Here's an excerpt from my green sheet YouTube lecture video. The center of mass is the weighted average location of all the mass in a body or group of bodies. We're using this representation because we're concerned with the y-axis. So here, big M is just the mass of the compound object. So it's the mass of the hoop plus the mass of the rod, or M plus M. And then we have to do a summation. We take the mass of the hoop and multiply it by its distance to what we're considering our reference point or origin. So the center of mass of the hoop is right here at the geometric center because of symmetry. So its distance to what we're calling our origin is R plus 2R, or 3R. The rod's distance to our reference point is the center of mass of the rod, which is at its geometric center because of symmetry. So that distance from here to here is R. Don't confuse what I'm calling the reference point for center of mass calculations with what I'm calling baseline for energy calculations. So the location of the center of mass of this compound object is at a distance 2r from our reference point, which again is this dotted line right here, the bottom of the rod or the bottom of the object. All of this compound object's mass can be considered to be concentrated at that green dot. That's what we're going to call the center of mass, and that's the basis for our energy calculations. So if the center of mass is here at a distance 2r from our coordinate origin, when it swings down to its inverted position, the center of mass location is a distance of 4r, or more precisely negative 4r, because I'm calling this position the baseline. So from an energy point of view, the center of mass starts at what I'm calling baseline and ends up down here, negative 4r away from that baseline. So at this point, we know the rotational inertia, we know the mass of the compound object, we know this h subscript b value, plug in values, simplify, and this is our answer, 9.823 radians per second is the maximum angular position of this object when it's in the inverted position.